Chiller Training Outline Activities. Welcome to the Chiller Training Outline Part 1. In this session, we will guide you through creating effective and customized training plans for chiller equipment, ensuring operational excellence and minimal downtime. In this module, we will learn how to create training outline activities specific to each chiller equipment. Start by gathering detailed information about the chiller in your facility, including the make, model number, and all essential nameplate information. Refer to the user manual, service manual, electrical circuits, and spare parts manual provided by the original equipment manufacturer, OEM. Conduct a site visit and document all activities through video or photos, which will support you in preparing a thorough training activities outline, TAO, for each task. This approach ensures that any new or current staff member can confidently access OEM services, allowing the chiller to operate at peak efficiency with minimal downtime. This slide introduces the key components of a chiller. Starting with the suction flow, this is the entry point where the refrigerant enters the chiller. Moving to the compressor, the chiller's core, which compresses the refrigerant gas, raising its temperature and pressure. Next is the terminal box, housing critical electrical components that help control the chiller. The control panel enables the user to adjust the chiller's settings and monitor operations. The evaporator is where the refrigerant absorbs heat from the liquid being cooled. Finally, the display panel shows real-time data on the chiller's status, such as temperature and pressure. Each component plays a vital role in the efficient and effective operation of the chiller system. Here we have a large industrial HVAC unit, most likely a chiller, made by Trane. The unit is beige with a big black air intake filter on the front. It looks like it's set up in a mechanical room, based on all the surrounding pipes and equipment. There's also a small monitoring screen on the front of the unit, probably used to keep track of how the system is running. The image has a teal border with rounded corners, which adds a nice, clean finishing touch to the frame. We'll continue with more essential components of a chiller. The economizer, or expansion valve, enhances efficiency by pre-cooling the refrigerant before it reaches the evaporator. The oil tank assembly provides lubrication for moving parts, essential for smooth operation. The purge system removes any non-condensable gases to prevent efficiency losses and potential equipment damage. Next is the condenser, which releases heat from the refrigerant into the surrounding environment, converting it from gas to liquid. Lastly, the motor housing safeguards the chiller motor, protecting it from external elements. These components work together to keep chiller operation seamless across various applications, from air conditioning to industrial cooling. The image shows a large industrial chiller unit, which is commonly used in commercial or industrial buildings for cooling purposes. You can see a big compressor, a condenser, and an evaporator as part of the system. These components work together to circulate a refrigerant, which removes heat from the system and releases it into the outside air. The shape of the unit is rectangular and compact, designed for easy installation and efficient operation in mechanical rooms designated spaces. This slide illustrates the stages of a compressor. Compressors are crucial in chillers, and this diagram highlights how they function, showing both internal mechanics and a real-life compressor example. The text semi-hermetically sealed motor indicates that the compressor motor is sealed to prevent leaks. It's important to understand how many stages are in your compressor, as multi-stage compressors provide more efficiency in cooling. Pay close attention to each component, as understanding the stages in your compressor aids in performing accurate diagnostics and maintenance. Here, we see a large industrial condenser unit. Condensers are essential in refrigeration and air conditioning, as they cool the refrigerant and release heat into the environment. Key features include the condenser unit, which is the main cooling component, and fans that help cool the refrigerant. Piping connects various parts and circulates fluids, while electrical components power the condenser. The Trane logo is visible, showing this unit was manufactured by Trane, a leading HVAC company. This image captures the industrial setting of a condenser, often in mechanical rooms, highlighting the vital role of condensers in cooling systems. An evaporator is shown here, fully insulated to prevent heat exchange with the external environment. Its main job is to absorb heat from the surrounding area, causing the refrigerant inside to turn into gas. This process cools the space, making the evaporator essential in refrigeration and air conditioning systems. Insulation keeps the evaporator efficient by reducing unwanted heat gain, ensuring that only the desired space is cooled. Understanding the evaporator's role helps in maintaining desired temperatures within systems. This slide details the function of an economizer in a refrigeration system. The economizer is a device that increases efficiency by moving liquid refrigerant more effectively through the system. As refrigerant vapor is drawn into the economizer, the second stage impeller provides suction, which pulls the vapor, sending it back to the compressor. This action aids in refrigerant flow from the condenser to the evaporator, improving overall efficiency. The system benefits from energy savings, though there might be a minor reduction in cooling capacity. Economizers are crucial for efficient chiller operation. The diagram here shows variable guide vanes within a turbine. Attached to a rotating shaft, these vanes adjust the airflow, optimizing efficiency. Guide vanes allow control over air intake, improving the system's response to changing load requirements. Positioned by a lever arm, they can increase or decrease airflow into the turbine, aiding in performance adjustments. Proper control of guide vanes can make a significant difference in energy savings and overall system performance. On this slide, we see the inlet guide vane, IGV, assembly mounted on a centrifugal compressor's first stage. The left image shows the IGV assembly, while the right offers a front view of the IGV in a fully closed position. Understanding the positioning and role of inlet guide vanes is crucial for regulating the refrigerant flow, which directly impacts system efficiency and energy consumption. Guide vanes function. When the chiller starts, the refrigerant first contacts the guide vanes at the suction entry. At startup, these vanes should be fully closed. If they aren't, the chiller may trip or put additional load on the motor, increasing current use. Guide vanes act as a load regulator, adjusting the chilled water supply to match the evaporator set point. Unlike a thermostat, guide vanes do not turn the system off but maintain it in standby, ready for immediate response. For proper maintenance, regularly check and tighten all joints to ensure efficient performance. This slide illustrates the role of a burst plate or relief valve. Located on the evaporator suction side, this valve protects the system from excess pressure. If pressure in the suction line exceeds 15 psi due to blockage or other issues, the burst plate will rupture, venting refrigerant to the atmosphere and preventing system damage. The burst plate is a critical safety device, making routine checks important for system protection and longevity. Purging unit. The purging unit shown here receives vapor from the condenser, which enters from the bottom and rises to the top. Inside the unit, a compressor heats the coil, causing the refrigerant to condense, while atmospheric gases remain as vapor. The refrigerant then flows back to the condenser via a filter. As non-condensable gases accumulate, they are released into a regeneration tank where a carbon filter removes any residual refrigerant before venting. This cycle ensures the purity of refrigerants and the efficiency of the system. This slide focuses on the compressor and regeneration tank within a purging unit. The compressor compresses vaporized refrigerant, while the regen tank manages purged gases, aided by a carbon filter. Each part plays a vital role in maintaining refrigerant purity and system performance, especially in high-efficiency refrigeration applications. This component contains a motor, regulator, and heater, with specific operating temperatures. When idle, the sump temperature should be at 150 degrees Fahrenheit. During operation, it should maintain 120 degrees Fahrenheit. This temperature is required because journal bearings, used instead of ball bearings, need heat to function effectively, improving system longevity. This slide provides a guide on changing the oil filter in the oil sump. The process includes draining, waiting, and then switching to filter change mode. After removing the old filter and adding a new one, turn the sump back to run mode. This sequence ensures the chiller is adequately lubricated and runs smoothly, which is essential for reducing wear and ensuring efficiency. Maintain oil sump pressure lower than the evaporator. Rely on gauges over sensors for refrigerant pressure, as sensors are less reliable with fluctuations. Transducers are appropriate for oil pressure but avoid using them for refrigerant pressure to maintain system accuracy. To turn on or off a chiller, you need to follow a specific order. First, check the oil tank level, oil tank temperature, and CHWMP set point. Then, turn on the following components in order: chiller plant motorized valve, cooling tower, CHW pump and condenser water pump, and finally, the chiller plant. This control panel is used for equipment like pumps, chillers, and cooling towers. The panel contains indicators for three-phase power, RYB, and a green light to indicate a closed connection, on. To turn on the equipment, ensure that the three-phase power indicators are lit and the green light is on. Then, turn on the voltmeter and ammeter switches and check if their readings are normal or check with the multifunction meter. Procedure to turn on chiller motorized valve, cooling tower, CHW pump, CW pump, chiller plant. The machine is currently in the off state, as indicated by the red light glowing in the stopped indicator and the regulator being set to the off position. To turn the machine on, adjust the regulator to either auto or man mode, as per the requirement. If auto mode is selected, there is no need to press the green button. However, if man mode is selected, press the green button after turning the regulator to man mode. The machine will be considered fully on when the green light glows in the running indicator. This will happen once the VFD starts running at the set speed. The same steps can be followed to turn on other equipment. The provided image outlines the steps to turn off a chiller system. First, verify the green light is on in the running indicator and that the regulator is set to auto mode. If running in manual mode, the regulator will be at man. Then, press the red button to stop the system. Next, turn the regulator to O mode. Finally, wait until the red light glows in the stopped indicator, which indicates the VFD has stopped completely. Once all these steps are completed, you can turn off the rest of the equipment using the same procedure. Thank you for joining us on this journey through Chiller Training Outline Activities Part 1. We hope this course has provided you with valuable insights, practical knowledge, and a deeper understanding of the key concepts and processes that drive efficient chiller training outline activities. The upcoming topic is Chiller Training Outline Activities Part 2.